All right, guys, back with review number 9. All right, so let's take a look at review number 9. Well, I have some little system here, right? The bracket, pulley, ceiling, etc., right? Mass 3m and m, okay? So, first problem, right? Derive an equation for the speed of the block of mass 3m mass after it falls a distance m in terms of m, d, and any other physical constants. Okay, so let's do this on a separate piece of paper over here. Okay, so how are we going to handle this problem? All right, so hopefully you remember, right? There's many different ways to solve this, right? But I've kind of told you guys, you know what? The easiest way I feel is to treat, right, the two objects as one, right? And we're going to use Newton's second law to kind of solve. So this is really 3mg. It's the force of gravity that's pulling it down, right? That's the force of gravity pulling this way. But I also have the force of gravity of this guy pulling down that way. So here I have what? Just mg. So we're going to use Newton's second law. F net is equal to what? ma. So let's pick this way to be positive. So I have 3mg minus mg is equal to, well, this is now one object, so 4ma. All right, so 3mg minus 1mg is 2mg is equal to 4ma. Looks like I can slash and burn the m's. Looks like I can divide by 2. So g is going to be equal to 2a. So that's 2. That's 2. So my acceleration for this is just going to be expressed as g over 2. All right, but that's not what I want. I want to know how fast, what's the velocity of this guy. So I have to use linear motion. So v squared is equal to v naught squared plus 2ad. It started from rest, so that goes to 0. Right, so v squared is equal to 2. But luckily I have a, so I'm going to plug a as g over 2d. Slash and burn, so v squared is equal to gd square root. So, right, there is the speed of the 3m mass after it has fallen. That's a d, sorry, that's d, right? That's d, right? A distance d. So that's that guy right there. Okay. All right. So B. Okay. So B. Determine the work done by the string. So I'm going to draw this that I did before, right? 3m. That's m. And here's my system. The work done by the string, right? Well, on the system. The string is in the system. So no work can be done on the system. If it's already in it, it's work in the system, and only forces outside the system can do work. So with this particular case, the work done by the spring is a big fat 0, right? 0. Great. C. What is C saying here? All right. The acceleration of the center of mass of the object of the system has a magnitude of COM, center of mass. Briefly, it's explained in terms of any external forces acting on the system, why this value is less than g. All right, let's take a look. Let's redraw this like this. So there's my pulley. There's m. There's 3m. Here's my system. Center of mass would be, somewhere in there. Okay, so why is this less than 0? Well, what do I have? I have this pulley is kind of attached to the ceiling, isn't it? And if I had just the overall force, acceleration of the system, that's this Fg downwards, right, of the system. So look what I have. I have a force up in the air, and I have a force of the system down. So if I said F is equal to what? Ma, acceleration of the system, right? What do I have? Let's call this F up. Let's call this F down. So I would F up minus F down is equal to ma. Well, look, I have some sort of subtraction going on here, right? So guess what? In this particular case, this a has to be what? Less than g. Okay? So there is my solution to number 9. Okay?